Well, hopefully this will be the last lecture that we have, and I think we want to have one more session at least to discuss tutorial problems which have not been uploaded on Moodle, because I am sort of reviewing that, but hopefully it can be up later today. So what we are thinking is we'll meet once for discussing those tutorial problems, and if you think it's necessary, we can meet once more to just review everything that has gone on in the course so far, or if you'd like to go on a sort of a lab tour, that's another option available. So we can take you guys around, show some things that are happening in some of the other big optics things that are happening in the lab. So we can discuss that offline, but thinking after today's lecture we won't have anything on Wednesday, and Thursday we can probably schedule the tutorial session. Is that okay? Yeah. So Wednesday post Diwali recovery, whatever. So we'll just let that go. So and any further sessions we'll let you know. So hoping we won't have to meet again next week, and then I think we are so everybody is saying November 28th they don't have a problem for the lab viva. Is that decided? November 28th is the date for the lab viva. It could be 27 and 28, I think. No, we'll have to announce that separately. We may have to have two different sessions to accommodate everyone and those things. We don't want to crowd the place with all of you there together. So we'll have to do this in probably two batches, but we'll see if it can all be done on 28th, or we need to do that on 27th also. We'll let you know separately. Okay, welcome to Introduction to Photonics. The last few lectures we've been talking about nonlinear response of material to electromagnetic waves. So we looked at Chi2 process, that is based processes that are relying on the second order susceptibility, and lately we've been looking at processes that are based on Chi3, which is the third order susceptibility. So far we have looked at, so far we've been looking at processes, lately we've been looking at processes that are enabled through the third order susceptibility, Chi3. So we looked at four-way mixing, we looked at self-phase modulation, we looked at stimulated Bruin scattering, and today we will look at stimulated Raman scattering. So when we discuss stimulated Bruin scattering, we talked about interaction of a light wave. Ideal case, it's a monochromatic light wave that's scattering of what are called these acoustic phonons, which are nothing but acoustic vibrational modes that are present in the medium at room temperature, and because of part of that scattering is going towards the source. We looked at the specific case of how this is happening in an optical fiber, and we said that light is beating with the light that's incident, and that beating provides a change in the refractive index, and this change actually corresponds to Chi3 multiplied by the magnitude of the total field whole square, This is through a process what we call as electrostriction. So, electrostriction basically says that whenever you apply an electric field across a material, the material responds by changing its density ever so lightly, and that density change can actually be causing a change in the refractive index of the medium, and through that you could actually have scattering of light. And of course, we say normally you have scattering which is this sort of scattering is spontaneous in nature, but if that spontaneous scattering is generating this index grating, and it's allowing for more intense scattering, that is essentially if the spontaneous scattering is stimulating the backscatter further, then you have stimulated Brouwan scattering. And essentially when we are talking about this threshold here, this threshold is the threshold that we are defining for a stimulated Brouwan scattering. Okay. So, spontaneous scattering is happening at any power level, but stimulated Brouwan scattering happens only beyond a certain power level, at which the grating that we are generating is strong enough that you have a large reflection of or large backscattering of the incident power into this nu naught minus nu b, which incidentally is actually called the Stokes scattering. So, whenever it is a process where the part of the energy is given to the medium and you are scattering off with lower energy, right, that sort of process is called a Stokes process. And then of course, when we talk about Raman scattering, we will also talk about an anti-Stokes process, in which case it is gaining, the photon is actually gaining energy. So, that is what. So, the question is whether the spontaneous scattering can stimulate this Brouwan scattering. What we are saying is the spontaneous scattering has to be strong enough, especially in the backward direction, so that you can see this stimulated scattering. Okay. So, at lower power levels spontaneous scattering is happening, but there are not enough spontaneously scattered photons that can create that modulation of the electric field, which gives you that modulation of the refractive index of the material. So, you do not have stimulated scattering at lower power levels. Okay. So, we looked at this being a problem for so it is not so good for optical communications. It is a problem for optical communications, but we said it is actually a very nice way of picking up strain or temperature of the material. So, it is very good for optical sensing applications. Okay. So, you are fighting against it in optical communications, but you are exploiting it in optical sensing. So, now we will move on to this other topic, which is we'll look at stimulated Raman scattering. So, what is Raman scattering in the first place? So, when light actually is incident on a molecule, right, which is basically two atoms sharing a bond between them. We said it could be looked upon as two masses connected by a spring, and once again at room temperature, this is not at rest. You will have basically the atoms are bouncing around their mean position and the process stretching the string, and these sort of modes, the vibrational modes corresponding to this are essentially the phonon modes of the structure. Okay. And in this case, to differentiate it from what we were seeing previously in acoustic phonons, these are called optical phonons. Okay. So, to give you a feel, in the previous case we were looking at these vibrational modes of a collection of molecules, right, networked in this glass matrix. The entire collection, entire network vibrating, they both all of them are moving around, and if that entire thing is moving around, then we call it as acoustic vibrations. Whereas if it is just corresponding to the vibration modes of a molecule, you have a much higher frequency at which this vibration happens. So they are called optical phonons. So nevertheless, if you have a light wave incident on this optical phonon, you have scattering of light happening. In one case, let us say that molecule is at rest, okay, and this electromagnetic wave comes around, it can actually give energy to, because the electromagnetic wave can influence a charged body as in a case of a molecule, because the molecule is sharing an electron, that's what constitutes the bond of that molecule. So it's a charged body, so that electromagnetic wave can influence that charged body, and in this case it's actually it can give energy to this optical phonon, and then it can essentially scatter off with lower energy. So you are coming in with h nu naught, but you are scattering off with h nu s, where h nu s is lesser energy corresponding to compared to h nu naught. So where did the rest of the energy go? It went into exciting this phonon vibrational modes, or this what we call as the optical phonons, right. So that is one scenario. So we can represent this in terms of a energy level diagram. So you say, okay, your phonons, this particular molecule is at rest, but upon the excitation of your optical radiation, right, with the h nu naught, it's going to a higher energy state, and at that higher energy state, it's essentially giving off part of this energy to what is called this h nu phonon, right. It's actually it's giving some energy to the vibration mode, and then it's essentially scattering off with lower energy. Okay. So this process is the Raman-Stokes scattering process. Okay. And of course, this is not something that happens for every photon that comes around. Okay. so this is a phenomena that happens in let us say 10 power with a probability of 10 power minus 7, 1 in 10 power 7 photons is undergoing something like this. So it's a very unlikely event, but nevertheless if you look well enough you should be able to pick up this Stokes photons. So that is one process. The other process is, if the molecule is already in a vibrational state, that means it possesses this energy h nu phonon, then an incoming photon has an opportunity to suck that energy out of the system, and you can scatter off with even higher energy photon. So that photon, that process is called anti-Stokes scattering. So this is anti-Stokes scattering, and in this case what are we saying? We basically have this molecule at a lower level here, but because of phonons it is actually gone to a higher energy level, and from there whenever this optical radiation comes along with energy h nu naught, then you have scattering happening. So you have a transition like this. So you take that energy of the phonon, which is denoted here, and scatter off with a higher energy photon, and that is actually called the anti-Stokes process. So top one is the Stokes process and this is the anti-Stokes process. Okay. So this anti-Stokes component is actually very good for sensing applications, because one of the major reasons why a molecule will be in an excited state, in a vibrational state, would be temperature. So if you heat up the material, all these atoms are bouncing around their mean position, so it's all in a vibrational state. Okay. So if you have a hot body, some material with higher temperature, if you come around with a photon with energy h nu naught, it can actually take that energy, that phonon energy, and scatter off with higher energy, okay, which is what we are calling as the anti-Stokes. So by looking at the anti-Stokes radiation, you can actually tell what is the temperature of that particular material. Okay. So specifically, if you are counting the number of photons in the Stokes and number of photons in the anti-Stokes for a given power incident in that material, then you can actually look at the ratio of the two. So when you are looking at the ratio of the anti-Stokes scattered power over the Stokes scattered power, that ratio, since this scattering is inversely proportional to the lambda power of 4, that ratio can be written as lambda s over lambda as to the power of 4, and then exponential minus of h nu phonon divided by kBt. Right. Actually, I am not writing down the individual scattering probability, but if you do that and put them together, you get a final ratio like this. So that ratio of the anti-Stokes scattered power versus the Stokes scattered power is highly dependent on temperature. So it actually gives you an opportunity to measure the temperature of that material by observing this. Okay. So, that way this Raman scattering is actually a very nice tool for temperature sensing applications. Okay. So, that is one aspect. The other aspect is that this phonon energy is actually different, it is a characteristic of the medium, right. If the medium is actually a crystal, what do you expect? If it is a crystal, then it is actually a periodic arrangement of all these atoms, and so all the molecules are exhibiting similar properties. So, the phonon energy spectrum is going to be very narrow, meaning that phonon energy will be a very specific energy. Okay. But if it is an amorphous material, that phonon energy will have multiple sort of energy levels. So, it will be that phonon energy will be relatively broad in nature, right. So, what I am saying is this phonon energy spectrum is narrow for crystals, it is rather broad for amorphous material. So, by observing this Raman scattered radiation, right, if it is broad, then that H nu S can go into any one of those levels, right, it can end up in any one of those energy levels. So, that H nu S is actually a broad spectrum, right. By observing the Stokes scattered light spectrum, you can actually get some insight on the phonon energy spectrum, and by observing the phonon energy spectrum you can tell what sort of material it is, right. So, this is actually very good for material studies. So, the question is, are there any additional components due to the spin of the phonons? Very much, right. So, the vibrational modes could be just translational modes or rotational modes. So, there could be a lot of modes. So, that is what you are referring to as spin of the phonon, right. All those will have their own signatures in terms of the phonon energy that it possesses, all these different vibrational modes. So, by picking off the corresponding scattered photons, you can tell whether it is what is the vibrational mode also, whether it is actually corresponding to this sort of vibration or this sort of vibration and so on. So, there is a lot more to this than what I am explaining here, but this is just the basic principle. This is an extremely powerful tool to understand some medium. You given an unknown medium, and let us say it is a transparent medium, because if it is not transparent, light is not propagating very far. Okay. Let us say it is a transparent medium and you are asked to tell what are the constituents of the medium, what are the different things that are happening in the medium. Main thing you do is Raman spectroscopy. This is what is called Raman spectroscopy. You illuminate with one frequency of light and then you look at the scattered light spectrum, and from the scattered light spectrum you can tell things like these the phonon energy spectrum, and from the phonon energy spectrum you can actually classify all these different types of phonons that are present in the medium. And you can also imagine that I am showing one particular molecule for which the phonon energy will have one particular structure. In reality, that material may have multiple molecules, different types of molecules. Like even in a germanosilicate fiber, you have germanium oxygen bonds, you have silicon oxygen bonds, right? Each of those bonds exhibit a different phonon energy spectrum. They have a characteristic vibrational mode with each of them. So when you look at that scattered light, so we are saying, okay, I am illuminating with this frequency. Let's just talk in terms of frequency. This is my mu naught. Then when I look at my scattered frequency, I can have multiple components, nu s1, nu s2, nu s3 and so on, right. I can have multiple components. Each of those components are representative of a particular molecule in that material. And let's say I have mapped out all the phonon energies corresponding to all molecules in general. Then I have a clear fingerprint for each molecule. So if I say I am seeing a peak around this point, then you say this must be this molecule, right. So you can identify what are the different molecules that are present in that material. And not only that, you can also tell the concentration of those molecules. How? You look at the relative peaks, the amplitude of those relative peaks, that tell you what is the concentration of those molecules. So now you give me one material, I will tell you that these are the molecules that are present and these are the concentrations at which they are present. So I can completely map out that material. How amazing is that, right? So it's an extremely powerful technique in spectroscopy. So that's clearly one application that it's good for spectroscopy. Okay, and we also talked about sensing, temperature sensing. It's a very nice tool for that. We can use for sensing applications. And we have one more application, which is communications. So in communications, it could both be bad as well as good. It could be bad because, let's say I am sending information in different frequencies, like in wavelength division multiplexing, different wavelengths. If nu naught and nu s are both different channels in my communication system, this Raman scattering, what it does is it takes energy from mu naught and deposits in nu s, right. That means energy, the information that you are sending in one frequency, one channel, is actually imprinted on another channel. So that can give rise to crosstalk, right. So that will be a major limitation in communication, that it can give rise to crosstalk. But it can also be used to your advantage. How can you use it to your advantage? Now what if at the same time the photon is coming to this molecule, you have another photon at h nu s also coming in there, okay. If I have both of these there, then I am stimulating the transition and I am going out with two photons which are clones of each other, just like what we did in stimulated emission, right. So you have a possibility of stimulating this Raman scattering. Why is stimulation important? Because when you talk about spontaneous scattering can happen to any one of these energy levels, okay. But stimulated scattering what that means is whatever your photon energy you are coming in with is the same photon energy you are going out. You are getting a clone of that incoming photon, right. So, in that case you are able to amplify a particular wavelength channel. Okay. So, that is one amazing. So, you have a question there, yeah.
Sir, what is wave number in?
So, the question is what is the wave number for these phonon energies essentially. So, the wave number, I can't remember the exact wave number, it is 1000 inverse centimeters, something like that. I don't 500 inverse centimeter. I think it's about 500 inverse centimeter in fused silica. The phonon energy in fused silica, which is amorphous medium, around 500 inverse centimeter is I think the peak. Actually, what I do remember is the phonon energy frequency, right? The frequency, the shift in frequency that you have, where you have maximum phonon, that corresponds to 13 terahertz. Okay. 13 terahertz would be roughly about 100 nanometers in wavelength. Okay. So, you figure out what it is in wave numbers. I am not, so you can do that, right. So that this is for SiO2, and of course you would expect this to be different for different material. Silicon material has this. Okay. So, but what I was saying is you can get stimulated Raman scattering. And what does that mean? If you are able to get stimulated Raman scattering, what does that mean from this optical process? Amplification is possible here. So, this can give rise to amplification of light. And there is a very important aspect to this amplification. How do you differentiate this from what you did in this erbium doped or ytterbium doped fibers, those rare earth material? Do you see a difference between the two? So, yes, there are basically photon your photons that are controlling your transitions, and here there are vibrations. That is partially correct, but there is one more important thing that we have here, which is key. So there, it's a nonlinear process, right? So you need a certain number of photons to activate this process. So beyond that threshold only you can have this process happening in a consistent manner. But the key difference is
nu(s) can be greater than the incoming.
So nu(s) can, the frequency, the scattered frequency can be greater than the incoming frequency if you are looking at the anti-Stokes process, which is also a good point. But the key difference is that here we are talking about virtual energy levels. Okay, we are talking about virtual energy levels here. In erbium, ytterbium, neodymium, whatever that rare earth ion we were looking at before, we were talking about God given physical energy levels. From this orbital, it can go only to this orbital. It cannot go anywhere in between, right? There were some very specific energy levels that it can go to. Of course, there was an advantage in doing that, in sense that once it went to that energy level, there was a finite time it could stay there. That energy was actually stored in that orbital for a finite time, right? Which is in the order of 10 milliseconds for some of these rare earth elements. Here there is no physical energy level. It's a scattering process. It happens instantaneously. So there is no storage of energy happening anywhere. Okay. So that you would say is a disadvantage, because when we talk about stimulated emission, we say we want to build a population inversion, right? And the inversion you can build with a very high level if you had a very long excited state lifetime. Remember, those were the basic concepts that we learned a while ago. So here there is no storage of energy. So there is no concept of building an inversion and all that, right? So that's a disadvantage. But the key advantage is, because your energy levels are fixed in rare earth ions, you could get amplification only at very specific wavelengths. If you use erbium, you get amplification at 1550 nanometers. If you wanted amplification at 1 micron, you needed to go to ytterbium. If you wanted amplification at 1.3 micron, you'd either go to neodymium or praseodymium, which has specific energy levels corresponding to that. So you could not do it at whatever wavelength you want. But what about this? Here, where you get amplification is determined by what? Your pump energy, your pump wavelength. I said 100 nanometer shift we have, right? So if I want, so this is actually lower frequency. 13 terahertz is lower frequency compared to the incident frequency, or in terms of wavelength, it corresponds to 100 nanometers. So this corresponds to 100 nanometers in wavelength, right? So if I want gain at 1550 nanometers, what pump would I use? 1450 nanometers. If I want gain at 1560 nanometers, I come in at 1460 nanometers. If I want gain at 1300 nanometers, I'd come in around 12 and 1220 nanometers or so on, right? So because 13 terahertz is the frequency shift, but that corresponds to a delta lambda that is different depending upon what wavelength range you are operating at. But the key point is, I can get gain at whatever wavelength I want, provided I have pump photons, that are which has a frequency that is downshifted by, or rather higher frequency that's upshifted by 13 terahertz. That's the question.
What about the phase selectivity between the
So yeah, the question is, what about the phase? Well, we are talking about a stimulated process. So if it is actually stimulating like this, the outgoing photons will be both of the same phase. It's highly coherent process.
Can you explain that process, like how the energy is transferred from the signal?
So the energy is transferred provided you have an incoming photon with h nu naught arriving at a molecule with a phonon energy of h nu ph, right? At the same time, you have this h nu s also coming, okay, the signal photon also coming. If all of these happen together, then you have stimulated Raman scattering.
So the phase is that of the signal itself, right? Not the pump.
The signal itself, that's right. The phase is corresponding to the signal, right, in this case. Now, what is the probability of something like that happening, right? We are talking about a material with zillions of molecules. You come in with trillions of photons at h nu naught, h nu s, and what is the probability that both these photons come to a location at the same time? That's a very low probability, right? You would think. So to increase that probability, you need to have large number of photons of both your pump and Stokes, right? So you cannot have like one photon of pump going into this material, another photon at the Stokes going into the material, and you cannot expect them to come to a location at the same time to have this process happening. So you say, okay, more number of photons, the better the probability that you will have the stimulated scattering. But then that is counterproductive, right? So with the signal you don't have more number of photons. I mean, signal is already weak. Why would you want to get to an amplifier? Because you lost all your power in attenuation, so you want to boost that signal, right? So signal is already weak. I have very few photons coming in the signal. So how do I compensate for that? I need to have a much larger number of pump photons than what is normally necessary in the case of a rare earth ion. Rare earth ion with the erbium doped fiber, you guys did these experiments where with pumps of even few tens of milliwatts you were getting gains of 20 dB and so on, right? Here that's not possible. You need to have much more number of pump photons, so you have much higher pump power levels that are required to achieve that same gain. Okay, so let's just quickly do that calculation. I'm realizing I'm running out of time, so but just quickly do this and then let's see. So if I'm tracking the pump photons, if I'm tracking the signal photons along the length of the fiber, that obviously is going to get depleted at the rate of minus alpha s ps, where alpha s corresponds to the attenuation in the fiber, right? That's just the background attenuation that's going on, but it's going to be enhanced, the number of signal photons or the Stokes scattered photons. It's going to be enhanced at the rate of GR, and it depends on the pump intensity. So you have PP over A effective multiplied by PS. Okay, so this corresponds to the SRS process, the stimulated Raman scattering process. Okay, so it's getting enhanced at that rate, and you are losing photons due to just the attenuation in the medium. Okay, and similarly you can write an expression for the pump power, in which case you will be depleted by both your gain as well as your background attenuation in the fiber. But based on this small signal approximation, you can actually come up with a expression for the amplifier gain. Basically you neglect the attenuation component. Okay, if you have enough pump power, you can get a gain through this process, in which you can neglect that other component. So your amplifier gain due to this Raman process can be given by exponential of GR over A effective multiplied by PP naught. PP naught is the power that's launched into the fiber at the beginning of the fiber, multiplied by L effective. Why does L effective come into the picture? Because it's the power is getting depleted, the pump power as a function of Z is going to get depleted. So PP naught is the power here. So this will go down as e power minus alpha Pz. So the total gain is over a certain effective length. Okay, and of course if your actual length of the fiber is lesser than that effective length. Effective length we calculated it to be in the order of 20 kilometers, but if your actual length of fiber that is available to you is much lesser than that, that physical length is what you would put here. Okay. So, if you do some quick math to achieve 20 dB gain, which is a typical requirement. So, GR equal needs to be 20 dB, right. If you have, so we have GR in fused silica is 6 into 10 power minus 14 meter per watt. I should tell you, I will give you a perspective. The Brouillon gain GB, give you a perspective, is 6 into 10 power minus 11 meter per watt. So, Brouillon gain is actually 3 orders of magnitude larger than the Raman gain, right. So, but yeah, nevertheless, even with this number we can still get some work done, because if you say you have a fairly long fiber, let us say the L effective is 20 kilometers, okay, and like we calculated previously, the A effective can be in the order of 50 micron square. If you put all of this together to achieve 20 dB gain, if you calculate PP naught would work out to be about 0.2 watts. Right, it is about, you need about 200 milliwatts over a 20 kilometer long fiber. Okay. So, if you have a much lesser length of fiber, let us say if you have only 20 meters, if you have 20 meters of fiber, then the corresponding pump power you need is 0.2 into 10 power 3, that is 200 watts you need here to get 20 dB gain. You understand? So, there is actually much higher requirement of power in a erbium doped fiber. If you had 20 meters, you could get 20 dB gain with maybe something in the order of 4 or 5 milliwatts of power. But here you are having to go to much higher power levels, mainly because of the fact that stimulated Raman scattering is not a highly probable event. So, you need to have both your pump as well as the signal photons coming to a location at the same time. So, which is possible only when you flood that material with a huge number of pump photons. Okay. So, that is the, if you want to call that as a drawback, but the big plus point is that this amplifier can be set up at whatever wavelength you want, because we are dealing with only virtual energy levels. So, we are not limited by by specific energy levels as in the case of rare earth ions. Okay, I think we run out of time. I wanted to actually speak a little bit about acousto-optic modulators, but I can keep going on and on for another month. So, I'll stop at this point. I think this is enough. What do you think? Yeah. You're worried about studying all this for your final exam. So, so let's stop here, and we'll meet again, like I said, later this week for the tutorial session on Thursday. And if you want any lab visits, if you think that's going to help your understanding of some of these things, or if you want a review session, we'll schedule that sometime later this week. Okay, we'll communicate over WhatsApp on those things. Okay.